Good morning, good afternoon, good evening. My name is Yunhui Zhang. I'm a researcher from IBM Research. Today I will present D2A, a dataset built for AI-based vulnerability detection methods using differential analysis. This is joint work with my colleagues Srab, Bern, Luca, Eddie, Bo, Jim, Alexandra, and Zhong. So here are the contents I'm going to talk about. I will explain why and how we generate the D2A dataset. Then I will show a use case where we train the model to predict static analysis true positives for a better developer experience. Traditional static analyzers have been widely used to detect bugs and vulnerabilities. However, at the same time, they demonstrate some limitations. For example, they are known to generate a lot of false positives. As a result, the researchers are trying to address this challenge from a different perspective, and multiple data-driven approaches have been proposed. For example, they may treat programs as text and apply RNN. They may treat programs as images and try CNN. They may first convert programs into graphic representations such as AST or program dependency graph, and then try GNN. However, training such models require large datasets with good labels. When it comes to vulnerability detection tasks, finding such datasets is actually challenging. Let's look at the existing dataset first. This table summarizes several popular datasets. Most of the datasets are on function level, which is to assign label to just one function. However, the issue is that it may not contain enough context about how a bug may happen. Therefore, such datasets cannot be used for interprocedural analysis. Besides, most of the datasets are synthetic. They are generated based on predefined patterns. Such datasets are usually large with good labels. However, they do not represent the diverse behavior in real-world programs. Now, let's take a look at the datasets with real-world examples. Draper used static analyzer as the labeler, and the dataset is large. However, static analyzers usually produce a lot of false positives. Therefore, the label quality of such datasets is usually low. Some real-world datasets get their label from manual efforts, either from existing vulnerability database such as NVD or from manual reviews. Therefore, the label quality is usually good. However, such datasets are usually small due to the expensive manual efforts. Just like a recently reviewed paper said, lacking good and real-world datasets has become a major barrier for this field, which is why we want to create a large real-world dataset with better labels. In particular, we develop a fully automated pipeline based on the static analysis, so we can generate large datasets from real-world programs. To improve the label quality, we leverage the commit history and run differential analysis to identify issues that are very likely to be false positives. Here is a D2A example. We have label, bug type, bug location, bug description. We also have the bug trace, but here I only showed one step in the trace. Then we extract all the function appear in the trace. Finally, we save the static analysis output or bug report, which we will use to train the false positive reduction model. Here is an example of the bug report from Infer. As you can see, it contains bug location, bug type, description, and a list of steps in the bug trace. Okay, so this chart shows how we generate the D2A dataset. Our intuition is that some commits are code changes that fix bugs. So we identify such commits and run static analysis on the versions before and after such commits. If some issues disappear, they are very likely to be true positive. If an issue detected in the before fixed version appears again in a later version, they are very likely to be false positive because they are not fixed. Therefore, the input to our pipeline is just a Git repo. We first analyze commit messages using an NLP model trained on NVD database to identify commits that are likely to fix bugs. Then for each commit, we run the static analysis on the before fixed and after fixed version pairs. After getting the static analysis results, they are consolidated by the auto-labeler that runs the differential analysis logic. After that, the labeled issues can be used for model training. This table summarizes the dataset generation results. We run the pipeline on 6 programs, such as OpenSSL and FmpEG. In total, the static analysis successfully processed more than 11,000 version pairs and produced more than 349 million issues. After deduplication and label consolidation, we have almost 1.3 million labeled issues. Regarding the label quality, since there is no oracle, we have to validate the label manually. Because true positives are more valuable, we did a bias random sampling, focusing more on the positives. So in total, we include 57 cases in the manual label validation. Each example was independently reviewed by 2 reviewers. And the screenshot on the right shows a cross-sourcing tool we created for this purpose. And we found that this procedure was actually very expensive. This table summarizes the validation results. We did a bias sampling, so there are 41 positives and 16 negatives. For each category, we list the number of issues where manual review agrees or disagrees with the D2A labels. The label accuracy measured on all samples is 53%. However, if we sample according to the distribution of the dataset, the accuracy will be higher because the accuracy on the negatives are higher. Now let's look at the accuracy without our technique. So since all the issues are positive per infer, and the infer was correct on 20 issues, so the accuracy without our technique is 35%. Therefore, the differential analysis is helpful. Next, let's look at the use case of the D2A dataset, where we train a false positive reduction model to prioritize static analysis issues. So static analysis tools usually produce a lot of false positives, and these false positives greatly hinder their utilization in practice. Then our basic idea is like the following. So we treat infer as a black box and train a model. Then we'll apply the model and select the subset of the infer issues that are very likely to be true positive. Then developer can review these issues first and move to the remaining issues if they have time. To make that happen, we firstly explore whether the true positive and the false positive are separable. This figure shows 8 features extracted from the bug report. As you can see, the value of the true positives and the false positives are significantly different, which suggests a classifier may achieve good performance. So after several rounds of feature engineering, we came up with 25 features, and in total we tried 13 models. So this table shows the performance of the 5 best models on the libTIFF. Please refer to our paper for more details and the full results. But in summary, so without our method, there are 121 report issues, and only 3 are true positives. So developers will see a lot of false positives and may not want to review our findings. However, when augmented with our method, for the highlighted model, we select 17 issues where 2 are true positives. So if developers review these 17 issues first, they will see fewer false positives. Besides, based on the D2A dataset, we further created 4 bug prediction tasks, which are different from the use case we just talked about though. We apply the pre-trained models such as ZBird and create a leaderboard. If interested, please refer to the leaderboard webpage for details. In summary, our paper presents D2A, a real-world dataset for vulnerability detection tasks. It's a large dataset with better labels. We show the use case and create a false positive reduction model to prioritize static analysis issues for a better developer experience. And this concludes my talk. Thanks for listening.
Thank you. Hi, everybody. If you just joined during the last presentation, my name is Carolyn Seaman, and I'm the session chair for this session on defect prediction and automation. And I have with me Yun Hui, who was the presenter that you just heard in the previous presentation, and he is ready to take your questions. The first one, actually not a question, but from Sophia, suggests another data set of vulnerabilities and security patches that you might want to consider in your future work. So be sure to make a note of that. And then there's a question from Fahad. What criteria did you use to collect vulnerability fixing commits? Did you use keywords or something like that?
Oh yeah, that's a good question. So essentially, we train a model. So basically, using the NLP techniques. So the procedures like we firstly get the data from NVD dataset. So there are basically some links to the commits, and we extract the commits, and we also extract of other those commits that are not relevant to the bug fix. So basically, we have a small data set, and then we train NLP techniques. But more likely, it's I mean, the keywords definitely play an important role to identifying the bug fixing commits, but there are also other patterns. So yeah, so in a short answer, it's just like we leverage the NVD and train an NLP model, and then scan all of the GitHub commits and find out those commits are more likely to fixing issues.
And then Michael has a question. The vulnerabilities in your data set can, by design, all be detected by infer. What benefit over using infer can an AI-based technique trained on this data set provide?
Right. Yeah, that's also very good question regarding the intuition. So exactly. So infer actually covers a lot of bug types, and usually they reports maybe 100,000 issues for a particular version. But the pressing issue here is that infer actually produce a lot of false positives. So if we use directly using those outputs as the labels, so basically our labels will be a little bit off. So the one of the contribution here is that we were trying to suppressing the false positives. And the ML part, so the machine learning part is just like, so based on the data set, so there are multiple different ways. So we can using classical machine learning, we can use the deep learning technologies, but all of them require a good, large data set, then probably including those generated by the interprocedural analysis, because we need the context. So that's why we are using infer to generate the data set, but then we have another round of differential analysis and the heuristic from the GitHub commits histories to filter out something we think is more likely to be false positives. So we are trying to improve the label quality such that the downstream task of the machine learning part may have a better data set to work with.
Thank you. Fabio asks, actually references the Delta bench work proposed by Pashenko in ESIM 2017, the machine learning part of that work. If you're familiar with that work, can you say a little bit about the difference between that work and yours?
Yeah, so thanks a lot for the pointer. So so there are, this is one work is using the delta like or differential analysis. There is another paper from the ETH. So I think the technology wise, so they are maybe one difference that we besides the delta part, we also have the we get the signals from the commit history. For example, this for earlier commits issue is fixed, but later on, according to infer. But later on, so this same issue appears again in the later version. So that basically suggests that there are probably a false positive for infer. So we combine both parts and try to, we took the signals from both parts and try to suppress the false positives. So the ML part here is just like a use case. So the ML part is not novel per se, because there are a lot of existing work trying to, extracting features from either code, either from the static analysis outputs, and trying to identify the true positives and the false positives. But here we want to say that the things we treat the assay as a static analysis as a black box. We solely look at the outputs, and we're exploring whether it's possible to, figure out whether there are false positives by only looking at the outputs. So I think we are more general because at the end of the day, if we are applying another static analyzer and have a different set of the formats of the outputs, so the technique may also work. But of course, we didn't show that in this paper, but it's just like the focus here is the data set, and we're trying to improve the quality of the data set. And then we could use a different machine learning techniques for the vulnerability detection task. I hope that answered the question.
Good, thank you. The next question comes from Na. She says, I guess this data set focuses on semantic bugs rather than security vulnerabilities. Is that correct?
I'm not quite sure what do you mean by semantic bugs. So I think probably they cover both. Things the infer actually can detect more than 150 type of issues. So some issues are security related, security vulnerability related. For example, the buffer overflow, the integer overflow, and non-point dereference. And there are also the semantic. Again, I don't understand. I don't quite follow what's the definition for the semantic bug here, but I will interpret like it's non-security related. So there are maybe other like the memory leak, resource leak. Right. So basically, we rely on the infer, and the infer report a wide range of bugs. So some are security related, some are not.
Okay. So now in the chat, if you want to clarify your question a little bit, if Yanhui didn't answer quite what you were asking, please put something in the chat to clarify that. Okay. And now has another question. It seems that this data set has 30% or more false positives. Is it reliable to use this data set to train any AI technique?
That's a very good question. So, I mean, we are basically considering this data set as a step forward. So it's definitely not perfect, because the false positive is one thing. And so I would say we need to strive a balance between the size and the quality of the labels. So if we take a look at the data set available today, so as I basically presented in the talk, right? So if we compare all of data set and what's the implications from those data set, so I think this is one step forward. And the quality of the data set actually heavily rely on the static analysis, and things infer and the clone static analysis is still in active development. So perhaps we may get better labels if there are advances in the static analysis part.
Okay. And then Fabio, I'm not sure this is a question, but Fabio has an aha moment. So he says the idea is looking at more than adjacent commits, the vulnerability and fix commits, adjacent commits, and comparing them, but also adding static analyzers, but also later. Does that make sense?
Yes.
Is his understanding correct?
I think that's I think that's correct. So but besides the adjacent commits, right? So we fix versus like a bunch of commits that are probably relevant to the bug fixes. And during the consolidation stage, so essentially, so we first identify, we deduplicate the issues and see how many times a particular issue appears in the history. So it's not only one or two versions; it's like a list of versions. So then we, based on the patterns, when the bug appears and when the bug goes. So we try to to say, okay, whether based on this pattern, say if it appears in a later version, and then again, maybe 200 commits later it appears again. So that definitely should be a false positive. So
stop you there. We're off the air.